Hello again. Thanks for watching this video and studying your math with us. The purpose of this video is to derive the expression that proves that orbits sweep equal areas in equal times. This is known as Kepler's second law. Last time we learned that this orbit is in a plane, and that is important. That means we don't have to worry about z. Without loss of generality, we're going to call the origin the location of the sun. The planet is going to be at this and at this location P, and all we need to worry about is R, and we can have the direction vectors being, since they're in a plane, UR and U theta. So let's recall from our class notes when we were doing this kind of thing, we had expressions for UR and U theta, thus, and we could take the derivatives with respect to time and get expressions like this. And as always, r of t is equal to the direction that r is pointing times a scalar function. We also in class took the second time derivative of this, and we got radial components and angular components. But we learned last time, since this was in a plane, that the acceleration is directly proportional to the radial unit vector, and that means that this squiggly underlined business has to be 0. We'll use that in just a moment. We also can recall from COD Calculus 2 that the area differential in polar coordinates is 1/2 r squared d theta, and if we change the variables here to be with respect to t, it's going to be 1/2 r squared, and then this is going to be theta prime dt, and that's the same thing as saying that dA dt is equal to 1/2 r squared, and that is theta dot. Now if we take this expression that we've just spoken about and take the derivative yet again with respect to time, we'll use the product rule for derivatives, taking the derivative with respect to time, and we can factor an r out of this expression, and we have the same expression in the squiggly underline that was equal to 0. Since the second derivative of a with respect to time is equal to 0, that means that the first derivative must be a constant. This is the area that is swept out per unit time, so that is a constant. And here's a picture of Kepler's law. And so we have the area swept out at equal times is equal.